In this video, you'll watch a live class that I ran, which covers how to sketch the hyperbola, the truncus, and the square root. Enjoy. First things first, we're going to be looking at the so-called hyperbola. We're going to be looking at hyperbola, truncus, square root. Is this the first time for any of you doing any of these graphs? Just let me know either in the chat or off the call, off mute. First time. Okay, easy. So, first things first, hyperbolas. So, for those who are new to the class, I've got a bunch of screen shares. We're going to be looking predominantly at the screen share that has digital stuff in there. We may be doing some handwritten stuff. Okay, so general form of the hyperbola. Basically, looks like a fraction. You're going to have some dilation factors, A and B. You're going to have some translation factors, H and C. But fundamentally, like the basic hyperbola is just some function 1 divided by x. And it ends up looking like this. We have this sort of hyperbolic shape from the top right and the bottom left quadrants. The reason why we have this shape is because of our denominator of x. So you can imagine as x gets larger and larger, whether it be positive or negatively larger, you've essentially got a fraction that's getting closer and closer to 0. Now, if it's negative, it's going to be on the negative y value side. If it's positive, it's going to be on the positive y value side. But basically speaking, as your denominator gets larger, you should get closer and closer to 0. That's why it gets closer and closer to 0 as a y value. Now, the reason why it bows out to infinity when you get closer and closer to 0 is because when you start dividing by a smaller and smaller number, like 1 divided by a half, for example, gets you to 2. So as that number gets closer and closer to 0, you get closer and closer to infinity, and eventually undefined, because when you divide by 0, we don't actually know what that's going to be, whether it's positive infinity or negative infinity. So that's the basic shape that we're working with. We can apply transformation factors to that. So first up, some dilation factors. Dilation factor of A is typically seen as stretching along the y-axis, or you could say from the x-axis. Basically put, if you have a bigger number in your numerator, the y value should be bigger, right? You're multiplying by 3, at least in this case. And if your numerator is smaller, for whatever reason, than 1, it usually won't be, but just for the sake of argument, if you have a smaller numerator, the y value should be therefore smaller. You're shrinking along the y-axis. The b term, so if you have a factor in the denominator, it basically does the same thing, except you're going to see an opposite effect. As your denominator gets larger, you should expect it to shrink closer to the axes, and if your denominator has a smaller number associated with it, a smaller coefficient, then what you then have is an expansion. It gets further away from the axes. Okay. Reflection terms. The good thing about this kind of graph is that you typically only really need to consider one kind of reflection. The reason why is because when you put a negative sign on a fraction, mathematically speaking, you can rearrange that to be either in the numerator or in the denominator, so it doesn't actually matter where that negative sign goes. A reflection in the x is the exact same thing as a reflection in the y. And you can kind of imagine that, right? You've got some green one here. If you flip it vertically, then this part goes down to here, this part goes up to here. If you flipped it horizontally, this part will go to here, this part would go to here. It ends up looking identical, mathematically speaking and visually speaking. As for translation factors, these work the exact same way as you might expect a quadratic to work, where when you have x minus a specific term, you're then shifting to the right by that term. So x minus 1, you're shifting to the right by 1. X plus 2, you're shifting to the left by 2. Now, specifically, because we have asymptotes on this graph, what we find is that our horizontal translation term is going to set your vertical asymptote, whatever that happens to be. So when you're shifting right by 1, x equals 1 now becomes your new vertical asymptote. Shifting left by 2, x equals negative 2 is now going to become your new vertical asymptote. And then finally, vertical translations. Again, we have asymptotes here. So your vertical translation is going to purely be responsible for setting, in this case, the horizontal asymptote. So +1 means you're shifting everything up by 1, including that horizontal asymptote. -2 means you're shifting everything down by 2, once again, including that horizontal asymptote. Those are all the key features. Does anyone want me to elaborate on that so far? Or do you want to see an example of how it all comes together when you sketch it by hand? Okay, sketching. So, how we sketch? We're basically following these 5 or so steps. You can kind of do these in mostly any order. You know, asymptotes, then axes intercepts, or axes intercepts, then asymptotes. It doesn't really matter what order you do it in. Just sort of follow, as long as you're hitting the key features. You need to know asymptotes, and you need to know the axes intercepts, at least for this specific graph. So, we have an example here. We have a fully transformed type of hyperbola. You can identify that it's a hyperbola simply because it is something where you're dividing by x. My first recommendation in literally any type of graphing scenario, whether it be this function or any other, is to start by getting or rearranging your hyperbola, whatever the function is, into its general form. The idea being that you want to reveal all of the translation factors, the transformations, anything transformations related. For us, that just means taking any coefficients off of the x. So because we have 2x plus 4 here, when you factor out this common factor of 2, that's going to reveal the true horizontal translation. Does anyone need me to clarify why we have to factor this out? Like, is it clear why +4 isn't our real horizontal translation? Clear? Okay, that's good. Okay, so from there. Wait, was that a yes for clear or yes for clarify? Clear. Okay, that's good. Okay, next up, asymptotes. So the good news about how you rearrange this is that now you can very quickly identify what your asymptotes are. So +2 means a shift left. So that means x equals -2. That vertical line is going to be your vertical asymptote there. And vertical translation -1 means you're shifting down by 1. Hence, you're going to have y equals -1 as your asymptote there. Nice and easy, just reading it directly off the graph. Next up, axes intercepts. So, yeah, without any restrictions on your domain, your function should have both an x and a y intercept guaranteed. So, x-intercept, as always for any graph, you do y equals 0, and then you just rearrange. This literally ends up being a linear equation. So you'd add 1 to both sides, multiply, well in this case I multiplied by 2 first for some reason, and then the x plus 2. And this is just linear, right? Simplify, 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 x equals -1/2 there. You'll find that y-intercepts are usually a bit easier because when you sub in x equals 0, everything simplifies down pretty nicely. So far, we have our x and y intercepts and our x and y asymptotes. All we're going to do from there is sketch everything together. So I typically start by drawing the asymptotes out. So I'll draw my little cross and then drawing the intercepts that I need to cut through. And you'll find that when you have all of your key features, it makes it hard to draw this incorrectly. Because if you know that you have to go through all these spots, there's really only one correct way of drawing the graph. So I'll go to the handwritten section here to make that clearer. So just click around the cameras. Let me know if anyone has any trouble clicking to the handwritten camera. Drawing out our asymptotes. So we're going to have -2, going to have -1, like this. And that's how you start it out, right? Just getting your grid. Now, if you also know your x is -1/2 and your y is -1/4, I really should have drawn this bigger, huh? Okay, you know what, we're just going to draw it together better. way bigger. -2 is going to be all the way out here. -1 down there. We have our new grid. We'll call this spot -0.5. Call this spot -0.25. Now, because you have to hit these two spots, you know for certain that your curve has to cut through here. Right, it just has to hit those spots. From there, as long as you know that your hyperbola is symmetrical about the diagonal, then all you do is you just mirror that curve down here. So you finish that off that way. So again, hit all your key features. This will inform where you put at least the first curve. Then from there, the second curve becomes a bit more obvious. You just flip along the diagonal. For a clearer picture on what that looks like, double check the screen share. If there's any questions in that, leave it in the chat or hop off mute. More than happy to reiterate any key things there. If you do have a restriction on your domain, then all you're considering now is those endpoints. Endpoints, doesn't matter what function you're dealing with, you just sub in the start or the upper and lower bound of your domain into your function, whatever that happens to look like, and then you get the y values at those spots. So in this case, we have an x equals -3. If you sub that into your function, you're going to get y equals -3/2. Upper bound of 2, sub that one in, you're going to get 3/8 as your y value at that spot. Now, yeah, go ahead.
Is it possible to have an exponential value as your denominator for a hyperbola?
Exponential.
Or x to the power 3?
Oh, x to the power 3, that doesn't make it a hyperbola anymore. You're now looking at, well, x to the power of 3 specifically, I don't know the name of it. I know x to the power of 2 would be considered a truncus, and that would look a little bit different. I imagine x to the power of 3 would look like a hyperbola still, just based on the fact that it's an odd power. Let's have a look. I reckon the shape's going to be overall the same. So in the handwritten notes, I have, in the handwritten section, document camera, I have the CAS. We're just going to do 1 over x to the power of 3. Yeah, so it's just sort of a steeper hyperbola-like shape. I imagine if you were to keep increasing that power more and more odd, it would get steeper and steeper.
Right.
Yeah. Now, once you go even powers, that's when you get a different function, which we'll look at next. But as a quick sneak peek, if I put squared in there, suddenly that negative gets flipped over to positive because you're squaring your negatives. Cool? Okay. Back to this bit though. So you get your endpoints. Only thing now to do would be to label those coordinates and then give the correct dot associated with that. So when you have a rounded bracket, that's when you do an open circle. And when you have a closed bracket, that's when you do a full circle at that spot. If you have a sufficiently restricted domain, you might find that some of these values can't be touched anymore. Like if I cut the graph out like here, for example, it's not going to be able to hit those spots. Very unlikely though. But yeah, in summary, that's how we handle hyperbolas. You want to know your asymptote locations, and then axes intercepts you basically solve like you always have. There hasn't been anything too special there. From there, you just got to identify where the curve is going to go, whether it's top right, bottom left, or top left, bottom right, based on the reflection terms. Anything to clarify there? Hop off mute or leave a question in the chat. Otherwise, I'll go over to the next function, which is the truncus. Okay, truncus, I already gave a bit of a sneak peek there. You'll notice looks very similar to the hyperbola. Only major difference is that now you're squaring that bottom bit. And so you've seen this shape before. Effectively, all you've really done here is take all the negative part of your hyperbola and flip it vertically, because now when you square a negative, you no longer have a negative anymore. It's now going to be only positive. This will still become steeper just because of the nature of the fact that you're squaring a number now. So as the numbers get bigger, they get bigger faster, and as they get smaller, they get smaller faster. That's why you get a change in steepness there. But the basic memorization here is just flip your hyperbola to be to be only positive. So yeah, the factors all work identically. If you have multiplication terms, they will stretch it in a certain way. Bigger term means more stretch. Whether it be in denominator or numerator will depend on what direction it stretches in. It's not super necessary. In this case, you can only reflect in the x. In this case, when you have that negative sign on the top, you'll flip in the x. So instead of pointing directly upwards, you'll point downwards. The reason why you can't flip in the y is because you're already symmetrical. So you can see if I were to draw a horizontal line anywhere on these spots, you'll notice that I hit, it's equidistant. So flipping does nothing. Mathematically speaking, you would put the negative directly on the x. And whenever you square a negative, it goes right back to being positive. So when I say directly on the x, I mean inside of the brackets of the square. That's why we don't end up having any actual effect when we reflect in the y. Translations, exactly the same. Horizontal translation is giving you the vertical asymptote. If it's negative, it goes right. If it's positive, it goes left. And vertical will also set your horizontal asymptote. So up, down, positive, negative. Nothing has actually really changed there. Sketching it, as you might imagine, is also quite similar. You still want to know asymptotes, you still want to know axes-intercepts. So once again, we're going to try and rearrange to make sure we can clearly see what those transformation factors are. So this one is slightly trickier because you need to know your index laws a bit better. But fundamentally all you're doing is taking this coefficient of 3 out the front, and I've gone a step further by taking it out of the square as well, which means you have to square it on the way out. Is anyone unclear as to how that works? I'll leave a question in the chat. Or hop off mute. Asymptotes, as always, look at your translation terms. This x plus 2 means you're shifting left by 2. So you've now got a vertical at x equals negative 2. The plus 2 at the front is a vertical translation, which means your horizontal asymptote is going to be y equals 2. Now, for the truncus, you're not necessarily guaranteed to have x-intercepts. If we scroll all the way to, well, any of these, there's actually an asymptote on the x-axis. It never actually touches. And so you're not necessarily guaranteed to have any x-intercepts. You will have a y in almost every case. The only times you won't have a y would be like with the default one, any vertical only transformations. You can see there's also asymptotes here. So look at these vertical ones only. You're never actually going to touch that. But if you do try to find it anyway, you'll just run into an issue where you're trying to square root a negative number. So set y equals 0, as you always would. Rearrange, so subtract 2 both sides. Divide by 2 times 9. And multiply to get the denominator over to the other side. Divide by negative 9. You get to this stage here where you're now trying to square root both sides, but you can't square root a negative number. So under those circumstances, you say there is no solution, hence you're not going to have any x-intercepts. And you'd kind of know this already if you're familiar with the graph. This is a positive truncus, and you're shifting it up by 2. If you just sort of picture that in your head, it would look like this. And so as you get more and more familiar with the function, you'll be able to recognize when or when not to bother trying to solve for a particular intercept. Y-axis intercept, again, x equals 0, simplify, simplify, and then you just put all the key features together. So in this one, yeah, in this one, even with just that y-intercept, you can still pretty pretty clearly only draw this one possible way. So you draw your grid, like I've shown you before, with your two asymptotes. And because we know that 37 over 18 is bigger than 2, the only way you can draw it is if you put this in quadrant 1. Or at least, quote-unquote, quadrant 1, if you think about this as your new axes. If you put this in that spot, then the only other way you could possibly put it is directly left, because it's now a truncus. Once again, a domain thing. We've discussed this before. Nothing's actually different. Rounded brackets is going to mean an open circle, and square bracket is going to mean a dark circle. Still just subbing in points, grabbing the y values, and so on. Anything to clarify there? Hop off mute or give me a question in the chat. If not, we can move on to square root graphs, which will be a little bit different. Okay, so the basic square root graph looks like this. So one thing to note specifically with the square root graph is that in math methods, we're in the business of sketching functions. The reason why I mention that is because the square root technically has two solutions. It has a positive and a negative solution. If you were to draw both, you would now have a relation, not a function. Difference between a relation and a function is simply, do I have multiple y values for the same x? Like if I sub in x equals 3, do I get two possible answers? And in this case, I do. I get y equals whatever that is, and y equals whatever that is. Root 3, basically. That's what makes it a relation. A function will only ever have one y per x. So any x value I give, you'll only touch this curve at one particular spot. So when we're dealing with a square root graph in math methods, we are only dealing with either the positive or the negative, depending on if there's a positive sign or a negative sign out the front of your square root. The reason why I mention this in that level of detail is because there will be something strange that comes up when you're trying to solve these things, and it'll make a lot more sense if you understand the background as to where this graph actually came from. But otherwise, we can look at some of the individual factors. Dilation factors do the same thing to every graph that they've always done. They stretch it. So a multiplication out the front, you're basically taking all the y values of the previous graph and then just shifting them up, multiplying by 3. So it's going to rise faster. And if you multiply by a number that's smaller than 1, then you're going to shrink. Same thing we've seen for all the other graphs. If the dilation factor is inside the square root, then you're going to get an opposite effect where smaller number means it stretches more vertically, and a bigger denominator means it's going to get closer to the x-axis. Understanding these things is less important for hand sketching, more important for your investigation sacks. These are the sacks where you'll have some generic function, like they'll literally even give you this, and they'll say, what does A do to the graph? What happens as I change C? These are the kinds of questions that you might get asked. This is why we're going term by term on each thing. Okay. Reflections, again, they've worked as they always have. If you have a negative sign out the entire function, that means you're flipping vertically. So you're flipping in the x. That's why when you see you've got a negative square root, you're going this portion of the root. When you have a positive square root, you're going this portion of the root. When you have a negative directly on the x, that's when you flip horizontally. So instead of pointing towards the right, you're now pointing towards the left. Now, this always gets questions. Why am I allowed to have a negative inside of the square root? The reason why is because you can have a negative variable, but you can't have a negative number. So negative x is fine as long as x itself is also negative. So for example, if I were to sub in x equals -4 into this, what I'm doing is I'm replacing the x part. with negative 4. Negative negative 4 is positive 4, which gives you the solution of 2. Technically it gives you plus minus 2, but as I said before, we're only taking the positive solution when we have a positive on the outside of our root. So it's for that reason that you are allowed to have a negative variable. You just can't have a negative number in the root. Do I need to clarify that anymore? Hop off mute or leave a comment.
Chris,
Yep.
when you state the dilations, right? What if you have both the A dilation and the B dilation? Like, let's say if you had like two outside the front of the outside of the square root, and then inside of it you had like x over 0.2. How would you like figure out like how much is dilated? Because that's like both is going to be stretching along the x-axis.
Mm-hmm. Yeah, so I mean, one thing you could do, so I'll go to the handwritten bit now, I've just rewritten that in the handwritten portion. One thing you could do is just look at the relative magnitude of these two things, and you could say this division of 0.2 is dominant, right? So you're stretching along the x-axis significantly more than you are stretching along the y. If you want to figure out the net result, which you typically don't have to do, but just for fun, what you would do is try to factor this outside of the root. And that's where you start using your index laws. So you would rewrite this as 2 root x over root 0.2. And then you just combine these two terms here. So the net dilation is going to be 2 over root 0.2 times root x. That you could consider as your net dilation factor along the y or from the x.
All right.
Does that answer that question?
Yep.
Yeah, so typically you don't have to do that. This really doesn't matter a whole lot for sketching it by hand, but if you got that in like investigation sac, it might say what is the dominant dilation, like is it going more right or more up? And in this case you would say more right because of that. This is way more dominant. Okay, back to screen share. So translations, again, work as they always have. When you have x minus a number, you shift right. When you have x plus a number, you shift left. In the context of the square root, what you're essentially doing is setting the x position of your vertex. The vertex being this sort of start point here. It would have been a full parabola, but we've cut it off. So we can still call it a vertex, but it's barely a vertex because we've only got half a parabola. But yes, horizontal translations you can think of as just shifting the start of the vertex, which now that I'm looking at my notes, I think this needs a bit of tidying up because this says horizontal asymptote. That is not a horizontal asymptote. Okay, I'm going to write myself a quick note to fix that. Translation root. Okay. Same thing here. Okay. Vertical, you're now shifting the y coordinate of your vertex. So +1 means a y of 1, -2 means a y of 2. And then obviously these things can compound onto each other if you have multiple translations in the same thing. So, sketching the square root, you're hitting many of the key features from before. So every graph is going to have axes intercepts. In this case, your starting point from the horizontal and vertical is going to give you your vertex, the x and y coordinate of your vertex, rather than asymptotes like I've erroneously typed. So we have a potential square root here, fully transformed square root. First things first, do some factorization, trying to figure out what is our actual horizontal translation. Take that 3 out the front. From there, you can clearly identify this as a shift right by 1 and a shift up by 1. So our starting coordinate, the vertex of our root, is going to be 1, 1. From there, axes intercepts. It's pretty common for your square roots to just flat out not have any axes intercepts. If you look at a few of the pictures from earlier, this barely has one. This has only got an x, and these are barely touching the origin. So it doesn't take much for it to just not have anything, full stop. So a good rule of thumb here is to try to visualize what the graph is likely to look like before trying to actually go ahead and solve things. Like we're seeing here, we're shifting right one, up one. So we're already in quadrant 1. If I go to the handwritten section and just draw 1, 1 as a point, we're already starting up here. And there was a reflection at the front of our, there's a negative sign at the front of our root, which means it's just going to point down. So without even solving anything, we can already tell that our root is going to look basically like that. There's no point trying to bother solving for a y-intercept. So these are things you can do to save some time once you get more and more used to how it all works, basically. Okay, from there. Yeah, if you do try to... Okay, now this one did have an x-intercept. So as always, set y equals 0. Back on the screen share, I should say. Rearrange, rearrange, rearrange. Square both sides. Now, we'll look at this in a bit. When you square both sides, you'll find some weirdness. But for now, it's pretty good. Squaring both sides, rearrange, rearrange. X equals 13 on 12. Makes enough sense. X equals 0, if you try to solve for that, we've already seen beforehand with our rough sketch, it shouldn't touch. And sure enough, we're going to get square root of -3 in there. If you're doing special, you might want to do something with that. That is considered a complex number. For us in methods, we're not particularly fussed with this, so we move on. Endpoints, we've touched that already. And you can see more or less that's what we end up with. Yeah, again, endpoints, sub in your values for what they should look like. We already know what happens at x equals 1, so we don't have to redo that. And so you just cut off your graph if you at all need to. That's one run through of a sketch. Any questions on how we got to here? I'll just take a sip.
I just have a question.
Mhm.
So inside the for the function f of x,
Mhm.
so inside the square root it says 3x minus 3.
Yep.
So the 3 in front of the x, is it like, does that do any like translations, or is that just the...
That 3 in front of the x, because it's a multiplication, is basically this. So it's worth noting division and multiplication are just two sides to the same coin. If I go to the handwritten portion here, one thing I could say is 3x, right? 3x would be one way of representing that. Alternatively, I could say x divided by a third. So whether it's division, whether it's multiplication, it's basically the same thing. The only reason I wrote it as a division here is because that will tell you the actual dilation factor if you had to say what the factor was. This dilation factor would be a dilation factor of a third, either along the x or from the y. So even if you see 3x there, that is the same as this. You do need to give it as a division when it's x. That's why it's written that way. So long story short, any multiplications on your function are dilation factors, not translations. Now, when you're stretching things, that sometimes effectively just moves the entire graph in a certain direction, so kind of translates. But as far as what we call them, like using math methods terms, you consider that a dilation, not a translation. Is that cool?
Yep.
Sweet. Okay, any other questions? Let me know. Otherwise, we can move on and talk about one of the weird results that comes with this square root. So, we're going to try and sketch this square root. It's a nice and simple one, just to make it easier to start with. Square root x plus 1. Only thing that's going on there is we're shifting up by 1. Shouldn't be anything crazy. Shift up by 1 means you're starting at the coordinate 0, 1. Let's go ahead and try to find some axes intercepts. Now, if you think about what this should look like, square root x normally points up and to the right, so shifting it up by 1 should mean we don't touch the x-axis ever. If I were to draw a quick version of that on the handwritten notes, I'd have my axes, I'd be shifting up by 1, and I'd be pointing in that direction. Shouldn't touch the x. And yet, if we try to solve for an x-axis intercept by setting y equals 0, we will find one. If you go back to the screen share, y equals 0. If you subtract 1 from both sides and then square both sides, you're going to get x equals 1. Weird. The reason why is because, mathematically speaking, you haven't, or at least I haven't, put in precautions to avoid the fact that we're only caring about one potential solution of the root, not both. What you have found, or what I have found in these notes, is that when you find x equals 1, what you found is the intercept of the negative component that we aren't drawing. So this throws off a lot of people when they're starting with square roots. They'll be solving for things and look at the graph like, how do I connect it all? The math will lie to you here, because putting in the proper procedures to avoid this would just be, frankly, annoying. And so typically, just look at what the graph should look like, and from there, use your common sense judgment. Because it's very hard to avoid this sort of solution if you're just trying to turn your brain off and go through the procedure. Is it clear why we get this solution now and why it's not great? If so, we can now move on to some actual questions. So all these you can find under the miscellaneous graphs under the functions and relations module. Have a read up of those. They're all basically the same thing. The relevant chapter in at least Cambridge 1 and 2 is going to be 4A, 4B, 4C. Wait, sorry, I think it's 4A, 4B, 4D. Let me double check. Oh yeah, it's 4C as well, because the way they do 4C is they show you the... Usually this one gets skipped. They show you the full parabola, but because like most schools will skip this. But okay, let's do some questions. So, kind of hard to sketch these collaboratively. I think what I'll do is I'll see if I can pick out some of the interesting questions in here and just show you how you handle them. So everything in here in question 1 is just sort of, just sketching things, right? You're really only caring about looking for your translation terms. They will set your graphs. They'll set your asymptotes, rather. Now, one thing that is interesting to me in this chapter is something like question 5. So we're told that we have some graph that is x plus 3 divided by x minus 1, and we're told it is the same as this hyperbola. Any thoughts on how we can get from, because the first part of this is to show that, so prove that this is true. Does anyone have any idea how we get from left-hand side to right-hand side there?
Would we subtract the function?
Subtract the function? Depends on how you mean.
Like we bring the 4 over x minus 1 to the other side? Same denominators?
Yeah, so with the show that questions, the idea is that you don't use the equation as given to you. You're trying to arrive there without using both sides of the equation at the same time. So it would either be modifying the left to eventually look like the right, or modifying the right to eventually look like the left. That's how you're supposed to go about these ones. I will say, doing it the way you've presented, what you will do by doing that is get, I think, by the end of it, 0 equals 0, essentially. Which is fine, mathematically speaking, but just not the context of the question. I think someone had a point to mention.
Would you have to like rationalize the denominator?
Sure, tell me how to do that.
So would you move like the positive one to the other side?
Yes, that's what I was talking about before, which is
Okay.
you only want to focus on one side of the equation at any given time. So I'll say there's a couple of ways you could do this. One where you focus on the left, the other where you focus on the right. The easiest one would probably be to focus on the right, but you will need to know how to do it on the left as well. So just to show you an overall, like a overall technique for doing it, let's focus on that right hand side. So going over to the handwritten notes, I'm just going to copy down that right hand side. 4 over x minus 1 plus 1. What we might notice between the two things, in fact I'll even put the equal sign in there to show, is that one side has everything over the same denominator and the other side does not. So if I were to try and rearrange this to make it look closer to this, one of the first things I want to do is try to get this all over same denominator. Any thoughts on how I can do that?
Would you put 1 over x minus 1?
1 over x minus 1. So are you saying like 4 over x minus 1 plus 1 over x minus 1? You mean like that?
Yeah. I'm not sure if that's right.
It's closer. It's not quite mathematically sound though, because 1 is not the same as 1 over x minus 1. There is something we have to do to this numerator to make it equivalent. Any thoughts, anyone? I'll show some examples. 1 is the same as 1 over 1. It's also the same as 2 over 2, 3 over 3, so on and so forth. How can we use that in a similar idea here to make sure our denominator is x minus 1?
You can put it as x minus 1 over x minus 1.
There we go. Whenever you have something divided by itself, that equals 1. And we're going to strategically choose x minus 1 as our denominator because we want it to be in the same denominator. Now that they are the same, what do we do from here to make it look exactly like that right hand side? How do we add fractions?
You want to collect like terms on the numerators for the left side?
Yeah. So basically speaking, whenever you have two fractions that have same denominator, when you add or subtract, you basically ignore denominator, that becomes common to both, and then you just add across the numerator. So you're going to have 4 plus x minus 1, collecting those like terms as suggested, going to have x plus 3 over x minus 1, and sure enough, we've gotten to where we wanted to go. So that's the easiest way you can probably solve this kind of question. You focus on this one and then try to put it down to same denominator. Now, the reason why I say you need to know the other way, which is starting here and making it look like this, is because the context of the question is to say, sketch this. And if you were just told to sketch this, x plus 3 over x minus 1, in an exam, without any other context, I don't know what this is. But what I could do is rearrange it to make it look like something that I do know how to sketch. This is not currently, or at least an easy to identify hyperbola. This one is. These are the same as each other, right? These are the same thing. This, I can tell, has been shifted right by 1 and up by 1. This, I've got no idea. So the challenge then becomes, how do I make it look like a hyperbola? There's a couple of ways you could do this. The way I recommend is polynomial division. That's just because it takes all the guesswork out of it. There is some algebra stuff that you can do where you play with the numerator and then split the terms around. My personal preference is just do a polynomial division. So as long as you know how to do polynomial division, you'll be sorted for this kind of question. Now, polynomial division is a topic for a different class altogether. So if you haven't done that before, don't worry. I'm just going to show you briefly what that looks like now, and maybe have a read up on that or have a watch of the video so you can sort that out. first thing you do is take the biggest terms of both sides and divide them by each other. X divided by x is 1. You then take this result, multiply the entire left-hand side, and put that on the bottom. So 1 times x is x, 1 times -1 is -1, and the final stage of your division is to subtract. So x minus x is 0, 3 minus -1 is 4. Now, the way that you finally write this is you say x plus 3 divided by x minus 1 is the same as your quotient, which is the perfectly divided portion, 1, plus your remainder divided by whatever the divisor is. And the reason why is because that's the part of the division that couldn't be perfectly divided. This is just long division, but in the context of variables as opposed to just solid numbers. So if you haven't seen that before, that's fine. Just have a read up on it next time. Point being is you can go from this side to the other. And that's what you'll need to do, perhaps, in an exam scenario. Once you have that, that is literally just a hyperbola. Right by 1, up by 1, those are the asymptotes, so on and so forth. That's the same as, if you look back at the screen share, same as question 6, question 7, and even question 8, you don't even really need the calculator for. It's just kind of telling you to use it because why not? Is there anything people want me to go through in this chapter before moving on to the Truncus questions? In fact, I'll even just do a screenshot and then have a look at that and let me know if you want me to go back to it. Okay, Truncus, let's see, is there anything unique here? That's just sketching. That's just sketching as well. They've put some extra wording around it, but really it's just sketch this. And this is also sketching, but with the CAS. Yeah, nothing we haven't seen before here either. I'll do a screenshot of that. If anyone wants me to tackle a particular question, just sing out. Happy to go back on it. And 4D, anything unique here? Sketching, sketching, sketch. Okay, that's also all sketching. Cool. So screenshots of all of those. We do still have at least 10 minutes left of class. There isn't anything particularly new here anymore, so the remainder of this will just be going through any particular questions. I've sent some screenshots out there. If there's anything anyone wants me to go through specifically, let me know. Otherwise, I'm happy to just pick out some key examples of each, and we can try and do maybe at least one of each. So while you guys decide that, I will start by just picking one of these, and just interrupt me if you want me to do something different. So probably a good one for the root would be 2a. So I'll just copy this down to the handwritten section. Don't have to click between different screens. Minus root x minus 2 plus 3. That's our function. Okay. Any thoughts on how we can start to sketch that? I'll even do a screenshot of the procedure that we follow. All right, that should be in the chat now. What is step 1 of that procedure? What should we try and do?
Do we have to identify the asymptotes?
Does it say asymptotes?
Oh, no, rearrange, my bad.
Yeah, okay.
Rearrange to
So
general form.
now, is there anything that we should do for this one, or have we already got that?
No.
Yeah, we've already got it, which is good. it is step 1, so it's good to do a quick check to make sure we have that. Okay, so what's step 2 all about? What do you think we can start to do there? Look a starting point. Yeah, thanks, Pia. So 2, 3. Yeah, 2, 3 is exactly the starting point. So we can start to draw our axes. Then what we have is 2, we have 3, starting point. Nice. All right, what else have we got to do? See how the negative root shape is and find the x-intercept. Yep, so that's good, Pia. So the fact that it's negative means it's pointing downwards. And so that means you only have to bother trying to find the x-intercept. Who can tell me how we find an x-intercept?
You make y 0.
y0. Perfect. 0 equals negative root x take 2 plus 3. 3 to the other side, make it positive again. X take 2, 3 3 is a 9, plus another 2 gives you 11. And so I've drawn that quite poorly scaled, but point being that will cut through 11. That is actually it. So step 4 is literally just find endpoints. There were no restrictions on the domain, so we do just sketch it infinitely. And step 5 was just sketching the curve with all those key features. That is that one done. Okay. If anyone has any questions, let me know. Otherwise, I'll get started on a Truncus one. Okay. So let's try 3 over x plus 3 all squared. Minus 6. Yeah, that's everything. Cool. So once again, you've got a screenshot of the things that you're looking for. What are we going to do? Transformation factors, x minus 3 and y minus 6. Yeah, precisely. So you're looking at those translations. The fact that it's x plus 3 means it's a shift right. Oh, so hang on, shift left by 3. And the minus 6 means a shift down by 6. So that does give you asymptotes that are x equals minus 3 and y equals minus 6. I haven't given myself much space, so I won't draw that just yet on an axis. So we'll follow the next step of the procedure, which is what? What do we do once we have those?
Can you solve for the intercepts?
Yeah, solve for the intercepts. So that, as always, is just x equals 0, y equals 0. Just by looking at the graph, do we have both, one, or neither?
You should have both.
Yeah, both sounds good to me. Okay, so it doesn't matter what order you do it in. Let's say x int first, y equals 0, x plus 3 all squared minus 6. Add the 6, divide by 3, it gives you 2. 2 equals 1 over x plus 3 all squared. Multiply x plus 3 all squared to both sides. 2 bracket x plus 3 all squared equals 1. That's just a quadratic. We're getting low on time. I'll just cheat a little bit and grab that. So 3, 1, 2 bracket x plus 3 all squared equals 1, comma x. That's going to give you, yeah, 2 root answers. So I'm just going to say x equals plus minus root something, just for brevity. Okay, and then x-intercepts, sorry, we just did that one. Y-intercepts, we let x equal 0. And so let's do this up here. Y equals 3 over 3 squared minus 6. 3 squared is 9. 3 over 9 is a third. A third minus 6. And then whatever. That's y-intercept. And so putting it all together now, we have our asymptotes. So x equals minus 3 was that one. Y equals minus 6 is here. This is going to be net negative, so we can put it down here. So 3 minus 6, what's that? 18, 17 on 6. And because it's a truncus, positive truncus, it's going to point up, but we don't even really need to know that too much because we do already know our x-intercepts are going to be both negative because they were, well, plus minus these roots. There, and then you would just label these as your x's there. Yeah, that's about it there, really. Okay, and we're not going to have much time to do a hyperbola, but the good news is it looks basically the exact same as the truncus, except, well, you solve it the exact same as you would a truncus. It's easier math, and all you've got to do is make sure that you are flipped on the diagonal to achieve that. Okay, so how do we conclude? Yep, so as I said, these can all be located in the school, in the equivalent school spot for classroom under functions and relations miscellaneous graphs. I'll put a copy of all of them in the chat here if you want to go on with that once you're already, you're already in the groove of how this all works, so it'd be worth practicing more questions from it. Let me grab all of those. Bang, bang, bang. Drag, drop, got it. As for where to practice this stuff, if you're in the Cambridge book, it's pretty much all the chapter 4 stuff. So 4A, B, and D. And if you're Jacaranda, let me just find that. Jacaranda. Okay, you don't want 2, Jacaranda. What's that going to be? I've probably skipped past it, haven't I? Yeah, okay. Chapter 6. So we're talking like 6.3, 6.4. Alright, that's about it. If anyone has any further questions, feel free to ask. Otherwise, I'll let you enjoy the rest of your day. Take care, guys.